chairperson, and I'm Hoshi Kondo. I'd like to talk about fatigue crack propagation properties of submicron thick freestanding kappa films in vacuum environments. It is well known that vacuum effects are observed on fatigue crack propagation properties in bulk metals. Generally, the fatigue crack propagates mainly by crack tip blunting and resharpening in bulk metals. And in air, fresh surface oxidation occurs at the crack tip in loading process. This oxide layer prevents reverse slip in unloading process. So, therefore, at the crack tip, reverse slip occurs during cyclic deformation, leading to fatigue damage accumulation at the crack tip. In contrast, in vacuum, fresh surface oxidation is suppressed. So, therefore, reversible slip can easily occur at the crack tip. Moreover, rewelding of the fresh surface occurs at the crack tip. Hence, the fatigue crack propagation rate, DADN, in vacuum is smaller than that in air in bulk metals. We previously conducted fatigue crack propagation experiments in 500 nanometer thick freestanding kappa films. And this slide shows intermittent FESM observation results of fatigue crack propagation behavior in air. By applying cyclic load, intrusions and extrusions were formed, which penetrated the film in the thickness direction ahead of the crack tip. And then this fatigue crack propagated through these intrusions and extrusions. So, in the thin film specimen, fatigue crack propagation accompanied with intrusions and extrusions. And this mechanism is different compared to bulk metals, that is, crack tip blunting and resharpening. So, because of these differences, the vacuum effects on fatigue crack propagation properties in submicron thick films were unclear. So the purpose of this study is to clarify the vacuum effects on fatigue crack propagation properties in submicron thick freestanding metallic films. In this presentation, I'd like to talk about 500 nanometer thick freestanding kappa films. We conducted fatigue crack propagation experiments in air and vacuum, especially in situ FESM experiments were conducted in vacuum. Tested materials are kappa films with a thickness of approximately 500 nanometers deposited by electron beam evaporation. This is the orientation map of the film taken by EBSD. Black lines indicate grain boundaries, and twin boundaries were observed within each grain. The average grain size is roughly 900 nanometers. And after the deposition, we conducted sacrificial layer wet etching to realize freestanding film specimens. This is the specimen shape and dimensions. We introduced a single-side edge notch as a crack starter into the specimen by using a focused ion beam. This is a fatigue testing machine used in air and vacuum. We employed a piezoelectric actuator and a load cell. This is a freestanding film specimen. The loading mechanisms are shown here. Cyclic load was applied to the freestanding film specimen by transferring the displacement of the piezoelectric actuator to the specimen jig attached to the linear guide rails, as shown like this. And this is the specification of this machine. This machine is capable to apply cyclic load to the film specimen inside the FESM chamber. And this slide shows experimental conditions. We conducted the experiment under constant maximum stress and at a stress ratio R of 0.1 and at a test frequency of 10 or 30 Hz. And environmental conditions are as follows. The experiments in air were conducted in laboratory air and in situ optical microscope observations. And the experiments in vacuum were conducted below this pressure and in situ FESM observations. So now I'd like to move on to the result and discussion part. This slide shows the in situ FESM observation results of fatigue crack propagation in vacuum in lower delta K. This is a notch route. The observations were conducted at every 1,000 stress cycles and while holding a constant tensile stress at 0.8 times of maximum stress. By applying cyclic load, fatigue crack started to propagate, and fatigue damages or intrusions and extrusions formed ahead of the crack tip. And then the fatigue crack propagated through these intrusions and extrusions. So this fatigue crack propagation behavior is similar to that in air. Next, this slide shows fatigue crack propagation in higher delta K. This is a crack tip, and strip lines were widely observed ahead of the crack tip. And by applying cyclic load, fatigue crack propagated through these strip lines, and necking deformation were observed along the crack path. This result indicates that fatigue crack propagated in tensile fracture mode. Fatigue cracks in air also propagated in tensile fracture modes. So this result obtained in vacuum is consistent with that in air. On the basis of these experimental results, vacuum effects on the fatigue crack propagation properties were investigated. This is the relationship between fatigue crack propagation rate DADN and stress intensity factor range delta K in air and vacuum environments. In both environments, three trends were observed, like accelerated DADN, constant DADN, and decelerated DADN as delta K decreased. In this study, we classified these three regions into high delta K, middle delta K, and low delta K regions. Focused on the environmental effects, no significant vacuum effects were observed in high delta K region. This would be because the tensile fracture mode was dominant in this region. In contrast, in the middle and low delta K regions, vacuum effects were observed. The enlarged view of these regions are shown here. In the middle delta K regions, DADN in vacuum is smaller than that in air. In contrast, in the low delta K regions, by decreasing delta K, DADN in air and vacuum are reversed, as shown in these figures. Moreover, fatigue cracks in vacuum propagated below the fatigue threshold in air, as shown here. So this indicates that delta K threshold became smaller in vacuum. So to investigate the vacuum effects, the fracture surface observations were conducted, as shown in this slide. This is a fracture surface in the middle delta K region in air and vacuum at same delta K. On the fracture surface fatigued in air, relatively flat surface with sharp edges were widely observed. In contrast, on the fracture surface fatigued in vacuum, flat surfaces are rarely observed, and instead, blunt surfaces with fine roughness are widely observed. So this indicates that this indicates the presence of vacuum effects on fatigue damage formation process. Similar fracture surface morphologies are also observed in the low delta K regions. Based on these observations, the vacuum effects on fatigue damage formations are investigated. In the middle and low delta K regions, fatigue crack propagation accompanied with intrusions and extrusions. These intrusions and extrusions were formed by fatigue damage accumulation by irreversible slip. So, in vacuum, fresh surface oxidation would be suppressed in the intrusions and extrusions formation process. Therefore, reversible slip and rewelding would occur in the intrusions and extrusions. In these conditions, intrusions and extrusions growth rate in the thickness direction in vacuum would decrease, and therefore DADM decreased in vacuum. In addition, due to the rewelding of fresh surfaces at intrusions and extrusions, the fracture surface morphology changed. However, the vacuum effects in the low delta K regions cannot be explained only by these factors. So, to investigate the vacuum effects in the low delta K regions, fatigue damage ahead of the crack tip at near threshold regions were observed. This is crack tip in air and vacuum. The fatigue crack in air at fatigue threshold, intrusions and extrusions were not observed ahead of the crack tip. In contrast, in vacuum at the same delta K of the fatigue threshold in air, intrusions and extrusions were formed ahead of the crack tip, and then the fatigue crack propagated through these intrusions and extrusions. So these experimental results suggest that at near threshold, intrusions and extrusions formation would be difficult in air, and therefore DADN in vacuum exceeded DADN in air as delta K decreased, and the fatigue threshold, delta K threshold in vacuum is smaller than that in air. This is the summary of my presentation. We conducted fatigue crack propagation experiment in air and vacuum to clarify the vacuum effects on fatigue crack propagation properties in 500 nanometer thick freestanding kappa films. Summary as the results are shown in this slide, and this is that's all for my presentation. Thank you.